In this lecture we are going to talk about one final thing before we jump down to Taylor and Lorentz series for complex functions, and that is we are going to discuss about Cauchy's integral formula. So in our past lecture we learned about Cauchy's theorem and we applied it to different scenarios to derive new results, and this will be one of the last results that we'll derive using Cauchy's integral formula. So what is this Cauchy's integral formula? Actually it's a consequence of Cauchy's theorem itself. So let me write down the statement for this integral formula. So this will be a statement for this formula, and the statement goes as follows: let f of z be analytic interior to and on a simple closed contour, simply closed contour. Let's call that contour C. If this is the case, then at any point that is inside that or on that contour, point Z, the following relation which can also be translated as a formula holds. And the formula is that at that point, that is the point of interest. In case you get confused, you can always put a prime over here. That is the point of interest. This is equals to 1 by 2 pi I, the closed contour integral of f of, let's say, w minus z prime dw. This w is just a dummy variable. This is known as Cauchy's integral formula, and now we're going to see the proof that why this is so. So now we try to prove this thing. Okay, so proof. Let's draw our regions first. Let's say this is the contour of interest, or the contour that we first consider. Let's call it C, and we're going to traverse in the anti-clockwise direction, so let's give arrows in the anti-clockwise direction. And the function that we are considering, that is f of z, that function is analytic inside all the points inside this contour and on the contour itself. Okay, so this is our C, and let's say this is our point of interest Z. Okay, now what we can do is that using Cauchy's theorem we have seen that it is possible to deform these contours. Okay, so we are going to deform this contour, and we are going to make this contour a circle that is centered around Z, which has a radius of delta, like this. And let's say this is C0. By C0 we mean that the deformed contour or the very small circle. And again, since we are traversing the contour in the anti-clockwise direction, we are going to traverse this circle in the anti-clockwise direction as well. Okay, so now let's begin. So from Cauchy's theorem we deform the contour. So what we have mathematically is that this picture will translate into the following. It should be actually w, because I'm using w as a dummy variable. W minus z, which is equals to, obviously there's a dw, C0 w minus z and dw. That means that we have this arbitrary contour that is denoted with a red line, and by Cauchy's theorem this is equivalent to evaluating a contour integral on this small circle with a radius of delta, right? This is the thing. Now we are going to take this part over here and we are going to write it as follows. F of w minus z w, this can be written as f of w minus f of z plus f of z, right? We can do that because there's a minus and there's a plus, and we have w minus z, we have dw. Then we can break these parts, and if we do that we will have something like c of delta. It should be delta or c0, whatever you want to say, c0. We will have f of w minus f of z divided by w minus z, plus there will be another contour integral because integration is a linear operator, f of z w minus z dw, and another dw here. Now what we need to do is that we need to evaluate these two parts. So let's evaluate this part first. So what we can do to evaluate this part is that we can already see that there is this f of z thing, right? But we are integrating over w, so we can pull this f of z outside the integral because z is a specific point and we are just putting the value of z inside the function. So let's evaluate this part first. So let's call this the second part and let's call it the first part. So now we want to evaluate the second part. So second part, let's write it down again. We can take out f of z and we have this integral, right? And now what we can do, we can choose any kind of parameterization that is convenient to evaluate this integral. Now if you see that c0 is actually a circle, so it's most convenient to go to the polar coordinates, and it has a radius of delta as we mentioned before. So what we can do, we can parameterize this thing using this relation z minus w equals to delta e to the power I theta, and theta varies from 0 to 2 pi since the contour is a circle. So after this, z minus w is equals to this guy, right? Oops, sorry, it should be w minus z, not z minus w, my bad. So dw should be I delta e to the power I theta d theta. So put this information of this box over here. So you will have f of z 0 to 2 pi, you will have I delta e to the power I theta, and here you will have delta e to the power I theta and d theta. So what you have is, at the end of the day, it's 2 pi I times f of z. So this part is done. Now what about this part? To evaluate this part, we are going to use a theorem that we discussed in our last lecture, that is integration of, let's say, f of z dz is equal less than ml, where m was the upper bound and l is the length of the contour, right? We are going to use this. How? Let's see. So now what we're going to do, we're going to use evaluate the first part using this trick. So our first part, if we use this trick in our first part, it will become modulus of this c of 0, sorry, not c of delta, and it will be f of w minus f of z divided by w minus z, and there will be a dw, right? But this is equal and less than to this guy. F of w minus f of z divided by modulus of w minus z times dw and its modulus. Since w minus z was parameterized as delta e to the power I theta up here, now what we do is that we find the modulus of this thing to be just delta. So now we can use the fact that modulus of w minus z is just delta. This modulus of dw will come back to that later, but note that we were talking about an analytic function, that is f of z was an analytic function, right? So now in our hand what we have is the condition for continuity. So using the fact that f of z is actually continuous, what we should have is something like this. That means between these two the difference will be less than epsilon, where epsilon itself is very small, and for this small epsilon we should find some delta which is denoted as z minus or w minus z, whatever you want to write over here. Because this is a modulus, it really doesn't matter, and this delta is actually the radius of this circle, right? So from there you can actually guess the fact that this w is actually a point on that circle, on the perimeter of that circle. So this is coming from the continuity condition, that for some epsilon we will have some delta which is actually the radius of the smaller circle itself. So if this is the case, okay, if this is the case, then what happens? Then using this condition over here we can write, let's say this is 1, we can write 1 as equal less than epsilon. Why there is equal less? Well, because we are dealing with this delta where you have equal sign and there is a smaller than this difference is smaller than this epsilon, so that's why there is an equal less sign. In the denominator you have some delta, right? And finally you have this closed contour integral of dw modulus, which is nothing but the perimeter of that circle, right? And that is just 2 pi delta. That means 2 pi r, the radius of the circle, and these two deltas will cancel each other out. So what you have ultimately is this portion is equals to 2 pi epsilon. So this whole integration can take this value, this contribution over here, this first part, it's contributing some 2 pi epsilon thing, right? And this epsilon will go to 0 in the continuous limit. So when epsilon goes to 0, right, the contribution from first part will vanish. So if that is the case, then this guy will ultimately go to 0, and this guy will ultimately contribute a 2 pi I f of z, right? So finally what we can write, so finally we can write that f of z, that means 2 pi I f of z, is equals to the closed contour integration, where you have this f of w minus z, and there is this dw, and if you take this 2 pi I over here, it will be 1 by 2 pi I. This is the proof of Cauchy's integral formula, and there are more things you can do with it. That is, what you can do right now is that you can take the derivative of this formula. So for example, you want to take this first derivative with respect to z. This means df dz. Okay, so on the left hand side you write this, and on the right hand side you take the derivative with respect to z. If you do that, let's see what happens. You will have this dd of z f of w minus z dw. You might ask, why am I doing this? Why can I do this? Well, you are integrating over dw, and we are taking a derivative with respect to z. Okay, so that's why you can do it. So this is just 2 pi I, and if you take the derivative, f of w remains the same, dw is unaffected, w minus z will now become w minus z whole square, and there will be one minus sign first over here. Why? Because if you take this ddz of 1 minus w by z, it becomes minus 1 w minus z whole square, right? So that's one of the reasons that why this should be the case. That means you put out this minus 1, and this is the first part that comes. But however, note that this said w minus z, it was, I mean, a 1 upon w minus z thing, right? So you have to apply the chain rule. So next you need to multiply this thing with ddz of w minus z itself, so it will produce another minus 1, and these two will cancel each other out, these two minuses. So in total there will be 2 minus signs, and they'll cancel each other out. Okay, so this is one way to see it. So nothing pretty interesting so far. What you can write is that the value of the derivative, obviously there should be an integral sign. This is just 2 pi I integral of f of w minus z whole square dw. Now let's take the second derivative and see what happens. Can we find some pattern or something interesting? So if you take the second derivative, similarly this will become w minus z 3, there will be a 2, and there will be f of w dw. At this point you might be tempted to cut this 2, but let's not do that. Instead of 2, let's write this as 2 times 1, which is just 2 factorial, right? Now take the third derivative. If you take the third derivative with respect to z, you will find that there will be a 1 times 2 times 3 divided by 2 pi I, and you will have this f of w minus z by 4 dw. So if you continue this thing n times, then this would be the nth derivative, and you will have a n factorial by 2 pi I contour integral of f of w minus z n plus 1 dw. This is another useful formula that comes from the Cauchy's integral formula. So why are these useful, or why are we bothering with these things anyway? Because even though we started this theorem with a function that is analytic, we will often see functions that are not analytic inside a domain, or let's say we have some region and there are some points where the functions fail to be analytic, and we have to do integrations for such functions. For example, if you take a closer look at Cauchy's formula, Just look at the formula again. 2 pi I contour integral of, let's say, f of w minus z dw. Let's just take a look at this formula. If I take 2 pi I on this side, on the left side, what I have ultimately is that this is saying this integral will evaluate, by this integral I mean this one, this integral will evaluate a result of 2 pi I times f of z, right? Now think of this portion, this f divided by w minus z, as some function g of sorry, it should be w, not z. Let me dw, yeah. So think of this whole thing, this fw divided by w minus z, as gw, and this gw function has a singularity or such a point at w equals to z where it fails to exist. An example would be, let's take a very simple example. Let's say z divided by z minus 1, f of z, let's say. This f of z, which is denoted as z divided by z minus 1, fails to exist at z is equals to 1. And in terms of complex variables, we call that this fails to be analytic at z equals to 1. So let's say this is the point of interest, that is the point 1, and we are integrating this f of z along such a contour that encloses this point. And obviously, instead of this arbitrary contour, we can make a contour around 1 which is a circle, right? We can deform the contour as long as we don't hit any type of points that is like this. That means where the function itself fails to be analytic. Okay, so if I tell you that integrate this function, integrate this f of z dz around a circle, obviously I don't have to tell you that around a circle. I can just tell you that take any arbitrary contour that only includes this one singular point, okay, and evaluate this integral. So this is where Cauchy's theorem will be useful, because this f of z, which is written as z divided by z minus 1 dz, you can immediately find the fact that if you compare z with f of z, because just look at the Cauchy's formula over here, you can compare the numerator with the function itself, and the denominator, you can use the denominator to find the point, okay. So this will be nothing but 2 pi I, and what do? You put this f of 1, right, where f of z, okay, let's not write f of z, let's write f prime of z, or capital F of z, that's a better notation. So capital F, okay. So instead of z, you put z equals to 1, so this will be just 1, or you can even have z plus 1. So if you put 1, you will get 2. Okay, so this is how Cauchy's integral formula will help you to evaluate these contour integrals, and similarly this as well when you have higher powers. So this will be it for this lecture, and I'll see you guys on the next lecture, where we will discuss some Taylor expansions, and after that we'll discuss more about Laurent expansions, singularities, poles, and residues, and after that we're going to jump into residue calculus. Thank you.